We speak student.
Similar figures, a la Schmidt. We here at Shmup have been making great strides on our new shrink ray design. We just have to work out a few final kinks. But it sure has taught us a lot about similar figures, which are figures that have the same shape as one another, but not necessarily are the same size. Let's take the Bermuda Triangle, for example. It's rumored that any ship that sails into this part of the ocean instantly sinks. Well, let's say the Bermuda Triangle is 20 miles by 12 miles by 8 miles. And in order for his cousin, Little Bermuda Triangle, to be a similar figure, she would have to have the same exact proportions. If each side of the Little Bermuda Triangle is exactly proportional to the corresponding side of the real Bermuda Triangle, the two triangles would be similar figures. So if Little Bermuda is 10 by 6 by 4, the triangles would be similar, since each distance is exactly half that of the original. If Little Bermuda is 10 by 6 by 2, well, then our hopes are sunk, because while two of the three sides are half the length of the original, the final side's only a quarter of the distance of its big cousin. Well, another way to determine whether or not figures are similar is to check their angles. You said angles, people, listen up. If all of the corresponding angles in two triangles are the same, then the figures are similar. Like if this 35-degree angle matches this 35-degree angle, and this 45-degree angle matches this 45-degree angle, and this 100-degree angle matches this 100-degree angle, boom, similar. So we know that similar figures have sides that are proportionate and angles that are congruent. Why might you need to pop this information into your brain? Say someday you become an architect and you'd like to build a model of a proposed structure that isn't life-size. That'd be an awful waste of styrofoam. Now, let's say you want to know how tall an existing building is. Well, maybe you need this information to rappel down the side of some building, but we won't get too nosy on that one. Well, you can measure your own shadow. You know how tall you are, right? Now you can measure the building's shadow, and the proportion of actual height to the length of its shadow will be the same for you as for the building. So if you cast a 3-foot-long shadow and you're 6 feet tall, looks like the ratio is 2 to 1. So if the building casts a 20-foot-long shadow, the building's top must be 40 feet high. Same ratio, 2 to 1. If we look at these as triangles, we can see that we're dealing with right angles, and as object and shadow height increase, so does the imaginary hypotenuse. It's really just two similar triangles, and we can be sure that our determination of the building's height is accurate. You may now rappel down it with complete confidence. Good luck avoiding the searchlights.